Hello everyone, welcome back. In this video, we are going to introduce handwritten text recognition. MNIST is the starting point for handwritten digit recognition. But what's MNIST? MNIST stands for Modified National Institute of Standards and Technology Dataset. It's a modified version of the original NIST dataset, which contained handwritten digits from U.S. Census Bureau employees and high school students. The modification involved normalizing the images and making them more suitable for machine learning tasks. It's a set of 70,000 grayscale images, sized of 28 to 28 pixels of handwritten digits, that's 0 to 9, where 60,000 are images for training and 10,000 are images for testing. But why is it a good starting point? It is simple and structured. It has small images, easy to process, and it's a benchmark dataset, standard for evaluating machine learning models. It's fast for training. It works well even on CPUs, and it's a foundation for deep learning to prepare us for advanced OCR tasks. What about real-world applications? One of the applications of MNIST is OCR. OCR involves scanning documents, bank checks, and IDs. Another real-world application is digitizing handwritten forms, like surveys, exam papers, and receipts. Another real-world application is postal automation, recognizing handwritten addresses. Let's look at the minimum system requirement. MNIST can work when you have Windows, Mac OS, or Linux. If you have Intel Core i3 or equivalent, it will work. It can work on RAM of 4 GB and a storage of 2 GB free space will work. If you have Python version 3.7 or higher, MNIST will work for you. For libraries, you need TensorFlow, Keras, NumPy, and Matplotlib. GPU is not required. CPU training works fine, even though slower. What about libraries? As you said, you need NumPy, you need Matplotlib, you need TensorFlow, and you need Keras. You can install all of these at once by this command, pip install NumPy, Matplotlib, TensorFlow, and Keras, all in one command. Now that we have everything well set, let's load and explore MNIST. With this code, we will import MNIST and explore it. Let's run this code. Okay. When you run this code, we got these labels, 5 labels. We have 5, we have 0, we have 4, we have 1, we have 9. Because in the code, we had to show 5 labels. Now, we need to pre-process the data. What's pre-processing? During data pre-processing, we do normalization and reshaping. What's normalization? To understand what normalization is, let's write the code number 2. data is preprocessed. So what's happening? These are the pixel values before normalization. As you can see, we have numbers, large numbers like 154, 253, 90, 190. Have you remarked all these numbers are less than 245? After normalization, these are the pixel values. As you can see, they are between 0 and 1. All of them. So the normalization has happened. What about reshaping? We need to make sure pictures are reshaped. Why? Let's run the code to understand more about reshaping. Let's visualize labels in 3D. Or let's first visualize label in 2D. That's 2D. During reshaping, we change the image into 3D representation. So this is how it looks like. This is how 5 looks like in 3D. As you can see, it's normalized. It's between 0 and 1, the height. CNN, Convolutional Neural Network, requires a 3D representation. As you can see in the code, we're adding the third layer, which is 1 in this case because the image is grayscale. It's grayscale, that's 1. If it was an RGB, it would be 3. Now, after pre-processing data, after normalizing and reshaping the images, we need to create a convolutional neural network model for MNIST digit classification. This code has many keywords that we need to explain in detail in the following slides, like ReLU, softmax, Adam, sparse categorical cross entropy, and accuracy. In this code, we started by defining how we want our model to be. Then we compile it. Then we display the summary. So let's start by ReLU. ReLU is rectified linear unit. Does the word rectified sound familiar? Probably yes, because ReLU works like a diode rectifier in electronics. It blocks negative values and let pass positive values unchanged. This is where it blocks every negative value, and every positive value will pass unchanged. In neural networks, negative values can confuse the learning process. That's why ReLU has to block them. If a neuron gets a negative weighted sum, it might send the negative values forward, which can lead to instability. In the separate lesson, we'll compare ReLU to sigmoid to justify why we have chosen ReLU over sigmoid. That's in a different video. Now let's talk about softmax. Softmax is here to make predictions easy. What does it do? Softmax converts raw model outputs, also known as logits, into probabilities. It ensures all probabilities sum up to 1. It makes prediction simple just by picking the highest probability. For example, if we have the logits that raw model outputs as 2, 1, and 0.1, it will turn them into probabilities, and the highest probability will be the correct prediction. This is the formula for softmax. Now, ADAM optimizer. ADAM, adaptive moment estimation, is an optimization algorithm that helps neural networks learn efficiently by combining the benefits of momentum and RMS prop. RMS prop is mean square propagation. Momentum prevents the model from getting stuck or slowing down too much, while RMS prop prevents learning from being too fast, skipping important details, or too slow, lazy learning. Then loss calculation, sparse categorical cross entropy. Entropy measures uncertainty. For example, a fair coin, 50-50, has high entropy, that's uncertain outcome. But a biased coin, where you always get hit, has a low entropy. It has a certain outcome. You know you will always get hit. In machine learning, entropy quantifies uncertainty in a probability distribution. Now that we understand entropy, what's cross entropy? Cross entropy cross-checks predicted probabilities, that's model's guess, against true labels, the correct answer. Low cross entropy means good prediction. The model is confident and correct. But high cross entropy means bad prediction. The model is uncertain or wrong. What about categorical cross entropy? Categorical cross entropy, as opposed to binary cross entropy for only two classes, is used for multi-class classification problems. That's where each input belongs to one of many possible categories, like in MNIST, where we have 10 classes, 0 to 9. And the loss function helps the model improve by minimizing prediction errors. And what's sparse? Sparse means using integer labels like 5 instead of one-hot vectors like 0, which means no 5, this is not 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 5, this is 5, this is not 5, this is not 5, this is not 5, this is not 5. So this is called one-hot vector. One-hot encoding explicitly marks all categories, while sparse encoding simply states the correct answer. Sparse encoding is faster and more memory efficient. Why did we choose accuracy as a metric? Accuracy fits well for standard classification, where each image contains only one object. Each image belongs to exactly one class. The goal is to assign one correct label per image. Where do we use other metrics? We use precision recall and F1 when some mistakes are more important than others, and we use map when detecting multiple objects in an image. For example, while in disease detection, a false negative is worse than a false positive, in MNIST digital classification, all mistakes are recalled bad. That's misclassifying an 8 as a 3 is just as bad as misclassifying a 5 as 7. So now that we understand the keywords, we can train the model. This is the code for training, or this is the part of the code for training. And what's happening during training? There is a forward pass that the model takes an image and makes a prediction. Then second, we calculate the loss. That's comparing the prediction to the actual label. The third step is back propagation. That's adjusting weights using Adam optimizer to improve accuracy. Then number 4 is repeating this for all of the images and get one full pass through all training images. That's one epoch. Then repeat the epoch. And then the fifth step is validation step. After each epoch, the model is tested on unseen data. But what happens after the training? After the training, there's an acquired knowledge, also known as weight. I call it the knowledge pack. Weights are the only output we get after training. That's what the model uses for predictions and can be reused for future training. What are weights? Weights are the only output of training. They store all the knowledge the model has learned. They determine which features matter most in an image. How do weights work? Before training, the model starts with random weight. That's no knowledge. But during training, weights are adjusted to learn patterns using back propagation. During back propagation is adjusting weights using Adam optimizer, in this case because we're using Adam optimizer, to improve accuracy. After training, the final weights are the only thing saved, storing the model's knowledge. Weights in prediction. During prediction, the model uses saved weights, doesn't relearn. It just applies its stored knowledge. The trained model can make decisions instantly using these weights. Weights can be reused in the next training. Weights can be saved and loaded to avoid retraining from scratch. Transfer learning allows a model trained on one dataset to help with another task. Weights are saved using save weights and loaded using load weight. Let's train the model. Here's the code for training. Let's look at the code. This is the same code. This is the part for loading. This is the part for preprocessing, normalizing, reshaping to a 3D representation. And this is defining the model, also known as building the model. And this is compiling the model. That's creating the model. And this is to train the model. And this is to evaluate the model, and this is to save the model. History is used nowhere. Okay, so let's run the code. As you can see, the code has 10 epochs. And you know what's happening in the epoch. In every epoch, there's a forward pass where the model takes an image and makes prediction, calculate loss to compare prediction to the actual label, then back propagation, adjusting weights using the optimizer, and repeating this step 1 to step 3 to all the images. And this makes one epoch, but before ending the epoch, there's evaluation at the epoch level. So before leaving the epoch, the model is tested on unseen data, then it goes to another epoch knowing what to improve. This is it. It's the first. So at the end of every epoch, there's a self-evaluation, and there's accuracy measurement. And as you know, this happens at epoch level, and in the code, when the training is done, we will do model evaluate. That general, the model has been trained. Model fit is for training, and those epoch level evaluations happens during fit or fitting. And at the end, there will be when the model is trained entirely, this code runs model evaluate on unseen data, X test and Y test, and then the accuracy is printed, and then the model is saved to be used during the prediction in the next step. Evaluating the model. After the model is trained, its performance on unseen data has to be evaluated. Why? We need to measure accuracy to check how well the model predicts on test data. We need to compare training versus testing performance. That's to detect overfitting. Overfitting is when the model is doing well during the training, but it does bad on unseen data. What's X-test and Y-test? X-test is a set of unseen images that the model has never trained on. Y-test contains the correct labels for X-test unseen images. At the time you download the MNIST dataset, it comes with X-test and Y-test. So after training the model and evaluating it, we need to save it. And why do we save the model? To avoid the retraining. We don't need to start from scratch in the future. We need to reuse it. We load it anytime for prediction. And yeah, we need to deploy it to use it in real-world applications like live digit recognition in this case. Now that we've trained our model, evaluated it, and saved it, let's reload it to make live predictions. That's 5 with enough confidence. This is 4 with enough confidence. There are limitations of MNIST. It only recognizes 1 digit at a time. It has a fixed image size. It's grayscale. It lacks context understanding. And it doesn't support overlapping digits. That means if you have touching or connected digits, it may be misclassified or ignored. As a final takeaway, let's see what we've learned and how to apply it. We've learned preprocessing, how to normalize, reshape, and visualize handwritten digits. We've learned how to build and train a neural network using CNNs, Redu, Softmax, Adam Optimizer, and loss functions. We've learned model evaluation, how to check accuracy, loss, and avoid overfitting. We've learned live digit recognition, capturing real-time handwritten digits with the webcam, and handling confidence levels. How do we apply it? We apply this knowledge to improve real-world handwritten recognition, to extend the custom datasets beyond MNIST for better accuracy, and explore rotation invariant and color-based recognition. We'll deploy the model in applications like integrating it to mobile and web apps for digital recognition, and use it in IoT projects with embedded systems. We can expand it to more complex text recognition, like OCR for reading entire words, not only a single digit. Well, I hope you enjoyed the video. Bye for now.